Hello and welcome. This video talks about Bayes' theorem. Bayes' theorem not only is one of the most interesting topics in probability which uses some of its core concepts, it also becomes an important topic when it comes to tests, exams, and at times interviews. People often find it tricky and at times confusing. But if you continue to watch this video till end, you would find that you can solve very complex problems with ease. Let's get started. Now this is clearly beyond tossing the coin and rolling the die. If you've studied basic probability, you would know what happens when you toss a coin, what happens when you roll a die, but there are concepts which could be tricky at times. And that's where your examiners or interviewers try to differentiate between a person who just has a superficial understanding of the subject versus a person who's really understood the core concepts. Now before we move any further, let's understand why probability becomes so important when it comes to data. Probabilities lead us to distributions. And distributions, if I were to give a simple analogy, are like the maps for your data. So imagine a journey without a map. If you're not in a familiar territory, how would you proceed without a map? It will become very difficult for you. If you're dealing with the data and if you've been able to trace a distribution for that data, your life becomes much easier and you gain a lot of confidence in what you're doing then. So it's the foundation and it's the building block of your entire study of a given data. One recommendation: if at this stage you're not very familiar with the basics of probability, you can watch our other videos on probability, and it should not collectively take more than 20-25 minutes of your time. But it'll ensure that you have the right foundation to go ahead with this video. If you already are comfortable with it, just hang in for a while and I'm sure things will start making sense to you. Bayes' theorem is nothing but an application of conditional probability. This red rectangular space is known as the sample space. It is nothing but a collection of all possible outcomes of an experiment. And let there be events A and B. These are not disjoint events, they are overlapping. And the portion which is overlapping, that is, the portion which is common to both A and B, is known as A intersection B. Now, if we were asked, what is the conditional probability of A given B, which is nothing but what is the probability of occurrence of A given that B has already occurred. Now to simplify this, whenever you are dealing with the conditional probability, assume that the entire sample space has shrunk to the event which has already occurred. So now our sample space becomes this event B because we are only dealing with that portion of sample space where B has happened. Now that we figured out that B has already happened, where do we find A in this portion? That is nothing but the intersection portion. So you can simply write the probability of A given B as probability of A intersection B divided by the probability of B. Again, if you're finding it confusing, you might want to pause, rewind, and listen to this piece again. But if you're good, we are good to go. Likewise, if we were to estimate the probability of B given A, which is nothing but the probability of occurrence of B given that the event A has already occurred, again simplified by assuming that the sample space in this case as well has shrunk to A, and now you will look for the availability of B within A. And that is nothing but probability of A intersection B divided by the probability of A. If we slightly rearrange the denominators of these two equations, we arrive at this equation. Let's call it equation 1. Please make a note of it and refer back to it because we'll be needing it as we proceed. Now that we have arrived at a relationship between the two conditional probabilities, just one more rearrangement, shifting the probability of B from the left-hand side to the right-hand side, gives us equation 2. This is Bayes' theorem. Congratulations, we are almost halfway through. Let's spend a little more time and try to obtain a generalized case of Bayes' theorem. What you see on the screen now is a sample space which is nothing but a collection of three events A1, A2, and A3. And as you can see, these are mutually exclusive and collectively exhaustive. If that's a jargon, let me help you refresh. Mutually exclusive means that the occurrence of one event precludes or negates the possibility of the occurrence of other events. So like when you toss a coin, in a given toss you can either get a head or a tail. You cannot get a head and a tail both at the same time. And what is collectively exhaustive? Collectively exhaustive simply means that if you add up the probabilities of all these events, this will constitute the sample space. So if you add A1, A2 and A3 here, that will be the total rectangular space that you see. A1, A2 and A3 are also known as the prior probabilities. Now let's say there's another event B that occurs. And if you see, B has something in common with A1, A2 and A3. In fact, if we were to put it like this, the portion of B common with A1 is A1 intersection B, the portion of B common with A2 is A2 intersection B, and the portion of B which is common with A3 is A3 intersection B. But wait a second, if we add all these common portions, won't we arrive at B? Exactly. So probability of B is nothing but the probability of A1 intersection B plus A2 intersection B plus A3 intersection B. Now if you made a note of what we obtained in equation 1 on the previous slide, A1 intersection B can be written in this form, and so is the case with A2 and A3. So probability of B can be written in this combination. And if we were to generalize this equation in the form of an AI where I obtains values from 1 to n, it can be rewritten like this. Please note, sigma here is nothing but summation. So now we have a more generalized form of the same equation which can extend to n number of prior probabilities. It's time to put it all together. What we obtained in equation 2 was this. What we saw on the previous slide, which was equation 3, was this. If we put the value of probability of B from equation 3 into equation 2, that is in the denominator, this is what we obtain. And this is the generalized form of Bayes' theorem. But if you're finding it too heavy by now, you don't have to necessarily derive it every time that you have to solve a problem. Let's look at a problem and then let's see how this understanding helps us. So here's the problem. In order to manage the credit risk, a bank regularly rates each of its borrowers as A1 or A2 or A3 based on their credit history. A1 implies low risk and A3 implies highest risk. Risk means the chance that a borrower might fail to pay back the loan amount. Now this is the background of the problem. Based on the historical data, on an average, 30% of the customers are rated A1, 60% are rated A2, and 10% are rated A3. What are these? These are prior probabilities. It was found that 1% of the customers who were rated A1, 10% of the customers who were rated A2, and 18% of the customers who were rated A3 eventually became defaulters. That is, they failed to pay back. So in a way, this is the conditional probability that's been given to us. Now let's look at what are we expected to solve. If you randomly pick up a customer from defaulters pool, what is the probability that he had received an A1 rating? An important observation related to such problems. These problems could be really daunting if you read the entire problem and then try to work it out. It'll be better to break it into parts and take a step-by-step approach. Let's just see how we can do it. Step 1. What is being asked? Let's first be clear about what is being asked and let's make a note of it. This portion of the problem says, if you randomly pick up a customer from defaulters pool, what is the probability that he had received an A1 rating? And if we were to write, this is what is being asked. Given that we have made our choice from the defaulters pool, what is the probability that he had a rating A1? Interestingly, the moment you figure out what is being asked, you will find that the problem already contains a flip of it. I mean to say, when I'm being asked A1 given defaulter, defaulter given A1 will always be given in such problems. Let's have a look. If you read the text which is colored here, it says 1% of the customers who were rated A1 eventually became defaulters. Not only that you know it for A1, You also know it for A2 and you also know it for A3. It's clearly stated in the problem. This is the conditional probability piece which is known to us. What else is known to us? Based on the historical data, on an average, 30% of the customers were rated A1, 60% of the customers were rated A2, and 10% of the customers were rated A3. And these are the simplest probabilities. Prior probabilities, normal probabilities. Here we go. And notice that when you add these prior probabilities, they make up the complete sample space, which equals 1. Now, for a minute, let's go back to what we were doing when we were trying to derive Bayes' theorem. Did we not look at something like this? All we have changed here is that now the event B refers to defaulters. And we know the general form of Bayes' theorem. So all we are required to do, having noted down all the values that are available, is that put those values in the formula. Step 3 is just putting the values in the formula that we have already derived. What should be the numerator? This comes from equation 1, probabilities which are already given to us. What is the denominator? So it is nothing but the probability of being a defaulter. And in how many ways one could have become a defaulter is an intersection of defaulter with A1, 2, and A3. And finally, all we have to do is take a ratio of the numerator and denominator, and we arrive at 3.7%. Please note that we've discussed solving similar problems in our probability videos through a tabular approach. That's an easy approach, but somewhere that does not necessarily leverage onto the properties of Bayes' theorem. If you go back and try to put things together, it should be able to make more sense to you. What is the terminology that we normally use? How do we identify it's a Bayes' theorem problem? We would always be given certain probabilities which are called prior probabilities, such as rating A1, A2, and A3 in this case. And we saw that when you add these all up, it would always constitute the complete sample space. The second ingredient that will always be available will be a set of conditional probabilities. And we saw it's very easy to figure out if you first note down what is being asked in the problem. These will be the opposite or the flip of it. Coming to the last part, it is nothing but the posterior probability, as we call it. That is being asked. I completely understand that this is a tricky topic. And that's why a lot of people tend to look for shortcuts. They try to memorize the answers given in the book. But that's not the idea here. And like I said in the beginning, these are the kind of questions that are asked to find out whether your knowledge about the subject matter is at the surface or you have gone to some depth. Hope you liked the video. And if so, please give it a thumbs up and subscribe to our channel. Hit the bell icon so that you continue to receive updates whenever we upload a new video. And like I always say, knowledge gets multiplied when you share it. So share it with all your friends who might benefit. And I'm sure you will receive knowledge in return. Thank you for watching.